Hello and welcome to this video in which we show how to use a spreadsheet to do the analysis of a single replicate 2 to the k experiment. As an example, we will use the experimental data shown here. This is an experiment to determine what factors increase the productivity of a programmer. So we have the following factors. Factor A is whether the environment that the programmer works in is light or dark. Factor B is how much pizza the programmer receives. Factor C is the size of the cubicle. And factor D is how much Mountain Dew the programmer receives. We measure the programmer productivity in programmer productivity units, and that's the response variable that we'll have in the experiment. In the spirit of full transparency, I have to confess I made this example up, but I thought it was funny. The first step in doing the analysis is to compute estimates of each of the factor effects as well as estimates of each of the interaction effects. We can compute a factor effect by multiplying each response by the corresponding +1 or -1 in the column associated with the factor, and do that for every row that we have data for. So to estimate the effect for factor A, we take the -1 here, multiply it by the response that we got for this setting, take 1, multiply it by the response that we got for the setting of the different factors, multiply -1 by its response, and so on. In the spreadsheet, we can do this using the sum product function as follows. We select the settings for factor A, then select the column with our data, and put $signs in to make sure we'll always use this column for our data. And now we have to normalize this by a factor of 8. This factor of 8 depends on the number of factors that we're using in our experiment as well as the number of replicates. And in this case, because we have a single replicate and 4 factors, our normalizing factor will be 1 times 2 to the third, or 8. So this gives us our estimate of factor A. And we can compute the estimates of factor B, C, and D similarly. So this gives us the estimates of the factor effects. Now we need to compute the interaction effects. So let's begin by computing the interaction effect of factor A and factor B. To do this, we create a column of 1s and -1s by taking the corresponding value in the column corresponding to factor A and multiplying it by the value in the column that corresponds to factor B. And we do this for all the responses. Now we can just copy our formula over, and that gives us our estimate of the interaction effect between A and B. So now we'll do this for all of the second order interactions. So when we finish this, we have this set of factor effects, these 4 guys, and second order interaction effects, these 6 guys. I will not compute higher order interaction effects, that is third order interactions, which include interactions between 3 factors, or 1/4 order interaction, which includes the interaction of all the factors, because I'm assuming that only the second order effects are significant. To determine which of these effects are significant, we can create a normal probability plot of them and determine which ones fall significantly away from the line that represents normality. So for this example, we'll do the following. I will not narrate the creation of the normal probability plot since this is covered in a previous video. So this is our normal probability plot of the effect estimates. And you can see that most of our effect estimates fall on a straight line, which indicates that they're approximately normal. But I have 3 that don't. I have this one, which corresponds to a value of 9.366, or factor D, I have this one, which corresponds to a value of 7.56, which is factor B. And I have this one, which corresponds to a value of minus 11.6 approximately, which is this one. So basically from the probability plot, we find that factors B, D, and the interaction between B and D are significant, and that the other effects are not significant. The next step in the analysis is to create a linear regression model that relates the significant effects to the experimental responses. For this problem, the linear regression model would have the following form: y hat beta 0 plus beta 2, where beta 2 corresponds to the effect for factor B, times x2, plus beta 4, x4, where beta 4 corresponds to the effect for factor D, plus beta 24, x2, x4, where beta 24 corresponds to the interaction effect between B and D. Computing the coefficients in this model turns out to be surprisingly easy to do. Beta 0 is just the average of all the experimental responses. Beta 2, which is the coefficient that corresponds to factor B, is the estimate effect for factor B divided by 2. Similarly, beta 4, which is the coefficient that corresponds to factor D, effect estimate divided by 2. Beta 24 is the interaction effect estimate for the BD interaction divided by 2. So I can write out my model as follows. So this is our linear regression model. One way to check whether this model provides a good model for the experimental data is to compute the model residuals and verify that they are normally distributed. We can compute the residuals as follows. First, we compute the predicted value y hat. And we extend this formula to all of the response values. Now we compute the residuals by taking the response value and subtracting y hat. And this gives us our set of residuals. Now we create a normal probability plot of the residuals to check that they're approximately normal. If they are, then we can assume that our linear regression model represents the relationship between the factors and the response fairly well. And we can see that our residuals fall more or less along a straight line on this normal probability plot, which means that they are approximately normal, which means that our model appears to be a fairly good one that represents the relationship between the factors and the experimental response. The last thing we need to do is create an interaction plot. An interaction plot helps us see how to choose the factor values to maximize the experimental response value. In this case, since the significant effects are B and D, we'll create an interaction plot between B and D. To do this, we'll create a table and fill it out. Our table will have entries for values of B of -1 and 1, and it'll have entries for D of -1 and 1. To get this entry in the table, we will average all of the responses that have factor B set at -1 and factor D set at -1. These four responses, again, they have values of B -1 and D -1. To get the next entry in the table, we'll average all the response values that correspond to a value of B of 1 and a value of D of -1. To get this entry in the table, we'll average all the responses that have a B value of -1 and a D value of 1. And finally, we average all of the responses that have B and D values of 1. So now we'll plot each row of this table, and each row of this table will give us a line on the interaction plot. So here's our interaction plot. Because the lines on this plot are not parallel, we see that the values of factor B and D that optimize the response cannot be chosen independently of each other. In other words, if I were to choose a value of B that gives me the highest value of programmer productivity, it would be B is equal to 1. And I would be thinking about this point. But the actual optimum value depends on the value of D as well. And if D is equal to 1, then my value of 1 for B would not be optimum. In fact, if I choose a value of D equals 1, then my optimum value is obtained when B is equal to minus 1. So the idea behind an interaction plot is if these lines are not parallel, it means that the two factors interact, and I have to optimize them jointly. So this concludes this video on how to do this analysis using a spreadsheet. I hope you found it helpful. Thanks for watching.